Okay, so picking up where the last video left off, almost done, because if B has a force going this way, then C must have a force going the opposite way, fighting it. Otherwise the bridge will be moving. And there's an up and down. The only arrow we don't have is this one, but kind of like before, if I imagine this is beam CD, if it's pulling down and right and not moving, there must be a force pushing up and left. So the arrows kind of take care of themselves. If you watch some other people's videos, they have weird ways of doing this, but I like common sense, and it's kind of like it's like a cool puzzle. I like this thing. So what the heck is this? This is basically your answer key. You know you're done with the problem when you fill in every blank spot. When I know the force that is on beam AB, like imagine this beam here, it's being compressed because I already know the arrows are going in, then I want to know what force is acting on it. And here, this beam is being tensioned, meaning you're pulling on this force. How much force is on that beam? How much force is on this beam? And what's kind of cool is it kind of just trickles down. So step 5, our final step, is to calculate the individual truss internal forces, where all you have to do is use the sum of the forces in the y equal 0 and the sum of the forces in the x equals 0. Or these are both fancy ways to say force up equals force down and force left equals force right, which we've already kind of gone over. So basically, look at this. Once I get an answer for all these, I'll be done. Now, how am I going to get an answer? Oh, I should put the angles on here too. This was 40.0, and this one was 56.3 degrees. Okay, so that's going to be useful later. I don't have to care about here. And here's how you do it. You go one joint at a time. You can ignore all the other joints, because what's cool about this method is if the bridge is not moving, then each individual joint is not moving. So you get to ignore everything else. And you do your work and organize it. We're going to probably carry over to the back page, but I'm going to go after joint A first. Now, how do you decide what joint to go after? Well, I pick the joint that either has the most information I know about it or the least information I don't know about it. So look at B. I could figure out the up and down, but I have no idea on the left and right. D, I would stay away from D. I would never go to D because I don't know anything about D. I don't know the down, the left, the right, the angles. Here, it looks like I know an angle and I know an up force. I could probably figure this one out. But my favorite is A because there's only 3 things. I'm going to write this. Do you know what this one is? The force on AD, or FAD. This beam is the force on beam AB, FAB. So I only need to find out 2 things, and I know an angle and a force. So if I cover this up, on number 5, I'm going to go after joint A. And you're going to do it for each joint until you fill all these in. I actually will probably never even touch D because I'll find out all the other forces easier. Okay, on joint A, if I redrew it with everything I know, here's the A, here's an arrow going down, there's a 342.84 pound force here, and then there's an unknown sideways force. So I'm going to use this to solve for FAD and FAB. Now, the key is, I need my 40-degree angle. Once you get the hang of this, it's pretty easy. You can do this exact same thing on joint C after a while. Okay, so here we go. The key to this is I only know one number, right? My up force. My up force is 3,482. So I'm going to write my force up must equal my force down. Okay, so my force up is easy. That's 342.84 pounds. It has to equal my down force. And think about it. Look at this picture and think about what force is going down. The only force going down is this guy. But down, bad, it's going down and left. I wish I knew a way to take an angled force and turn it into its vertical part or its horizontal part. Hmm. Oh, look, an angled force that I turned into its horizontal part and its vertical part. Oh, I just got to do diagonal times sine or diagonal times cosine? That's right. Okay, so just realize FAD is a diagonal force. If I want to turn it into its down part, all I have to do is do diagonal times sine. Remember, sine is always the vertical part of 40. So it's just like this problem, except here I knew the diagonal is 45, and I used sine of 40, or sorry, sine of 64 to get its down force. And the difference with this one is I don't know the angle, but I can still say diagonal force times sine will make its vertical part. And then I just divide both sides by sine of 40. Can you do that? Heck yeah, you can do that. And FAD, my force of 8 on beam AD, is whatever 342.84 divided by sine of 40. And I get 533.36 pounds. 533.36 pounds force. So I already know one of my answers. 533.36 pounds of force. Awesome. Next, I'm going after FAB. But what's cool, now that you know the diagonal force, it's like knowing the 45. How did I find this guy's horizontal force? I took my known diagonal times cosine, and I got it. Well, I just unlocked what I need to get this, because since this pushes down and left, I can turn it into just how much left, and it has to equal the right, because force left must equal force right. So my force left is that 533, my previous answer, times cosine of 40 must equal my right force, which is FAB, or FAB. Okay, and I just typed that in. 533.36 times, cosine of 40. And I get 408.58. So 408.58 pounds. Boom, we're knocking them down. Now what's cool is you can pick either B or C to go after next. If you pick C, it will be almost the exact same thing we did. The only difference will be, instead of a 342, we have an 857. Instead of a 40-degree angle, we have a 56.3. So if you want to do that, do it. This is the force on CD. This is the force on CB. Now, me personally, I choose an even easier way, a little bit. We'll have to go to C eventually, but check this out. Focus on just B, right? Let me put this other force, force B, D. If I just looked at B, I'm going to draw this here, number 5 for joint B. I know a lot about joint B, because if I just redrew joint B, I would have this going on. Here's B. Here's a force up for FBD. Here's a force right for FCB. Here's a force down that I know is 1,200 pounds. And now I just figured that out. My left force is, now I can use that number, 408.58 pounds. So guess what? Your force up must equal your force down. Well, guess what? My force down is 1,200 pounds, and I only have one force up. I get to ignore everything else because joint B is not moving. So I'm allowed to say FBD must equal 1,200 pounds. Awesome. And then I have my force left must equal my force right. Okay, what's my force left? 408.58. What's my force right? FCB. I didn't need to use trig at all because they're just perpendicular lines. So I already know this answer is 408.58 and this answer is 1,200. So I only have one piece left to find, and it's this guy. Now you could either go after it up here, I don't recommend, or you could go after it here on joint C. Just because I don't want to flip the page and I want you to be able to see the picture, I'm going to do it right here. I normally would flip the page for this, but this is number 5 going after joint C. And this is our last one, and we'll have the whole thing done, which is pretty awesome. So if I just looked at joint C, let me draw it. You got F, C, D, the one thing I'm missing, going down this way. You got joint C right here. You got a force going up on that joint, which is 857.16, and you have a force going left that we just found out last problem. Remember this 408.58? So 408.58 pounds. So what's cool is you can either, remember at the beginning I had to use an unknown. I was like diagonal force times sine turned it into its down force. I could do that again here. I could do diagonal times sine to turn it into a vertical force. If that's the case, I'll use this 857. Or I could do diagonal times cosine of, what is this, a 56.3 angle. I could use FCD times cosine of that angle to make 408. It doesn't matter. You'll get the same answer either way. Me personally, I don't know why, but I like to do the force up equals the force down a little better. I don't know why. I just like to use sine. I'm a creature of habit. So my force up is 857.16. My force down, hopefully you can see when I write this small, is diagonal times sine of 56.3. Hopefully you can see that. Boom. So I divide both sides by sine 56.3, and I get FCD is, this got really tiny, I should have probably just turned the page, 857.16 divided by sine of 56.3. That turns it into its down part. 1030.30. That's my last answer. I know I'm done when this thing has an answer for each one of those blanks. So if you looked at this, if you applied a force right there, I would expect, and this is what's kind of cool, if all these beams were made of the same material, the same thickness, I would expect it to break where the highest force is. So when I look on here, the highest force is right here, 1,200 pounds. I would expect this beam to break first, followed by that beam, which has a second amount of force. Kind of crazy. You can kind of predict where your bridge will break if you apply forces to it. All right, well, I'll talk to you guys later. I hope that makes sense. Watch it again. Ask questions. Email me. Talk to you later.